In this film, we'll discuss conduction. Heat flows through objects from the hot to the cooler parts by conduction. The atoms of all substances vibrate continuously. As they are heated, they vibrate more vigorously and bump into their neighbors, transferring energy to them. Heat is thus passed through the substance and will carry on to cooler objects that come into contact with it. Unlike convection, the heated substance as a whole remains fixed, and the heat effectively flows through it. This experiment demonstrates the process of conduction. The 3 cups on this copper rod contain flash powder, which will ignite when the cups become hot enough. The rod is heated at one end. The flash powder ignites in sequence as the heat travels along the rod. The rate at which the heat flows through the substance depends on its thermal conductivity. Copper is a good conductor. In fact, all metals are relatively good conductors, but their conductivities do differ. This is shown in the next experiment. Equal-sized rods of iron, aluminium, and copper are evenly coated with wax. The copper is coated with red wax, the aluminium with yellow, and the iron with green. When the wax has set hard, the ends of the rods are placed in a water bath. The water in the bath is then heated to a constant temperature just above the melting point of the wax. All 3 rods receive the same quantity of heat. The heat travels along the rods at a rate depending on their respective conductivities, and the wax is melted. After a set time, the rods are examined. The amount of wax melted from each one indicates how far the heat has traveled along it. From this, we see that copper is the best conductor of the 3. Aluminium is next best, then iron. Even so, all metals are better conductors than non-metallic solids, like wood. This too can be shown with a simple experiment. This bar has wood at one end and brass at the other. A tube of paper is placed around the junction at the center, and the bar is passed several times through a Bunsen flame. Where the paper is in contact with the metal, it remains unaffected. But where it touches the wood, it becomes charred. This is because the metal conducts the heat rapidly away from the paper, which thus remains cool. But the wood cannot conduct the heat away quickly enough. All non-metals are relatively poor conductors, but different materials still have different conductivities. Our sensation of temperature illustrates this. A carpet feels warm to our feet because it's made of a poor conductor. But at the same real temperature, a tiled floor feels cold because it conducts heat away from our feet quite quickly. Like non-metallic solids, liquids too are poor conductors. This can be demonstrated with water. A small piece of ice is wrapped in gauze. It is placed into a test tube of water, and the gauze makes it sink. The water at the top of the test tube is then heated. It soon comes to the boil, but the ice at the bottom remains unmelted for several minutes. So water is shown to be a poor conductor. A similar experiment with ice in a test tube containing only air shows that air is an even worse conductor than the liquids. So we can divide materials into good conductors and poor conductors. The metals are good conductors, the best being silver and copper. Non-metallic solids, liquids, and gases are all poor conductors. Poor conductors are called insulators. The conduction properties of different materials determine some of their uses. Good conductors are used to transfer heat, to food for example, or to water in hot water systems. To heat water more quickly, the surface of the metal is sometimes enlarged by forming it into fins, as in this kettle. The same principle is also used in some kinds of water heater. Here the fins serve to conduct the heat rapidly to the water. But they can also be used to carry heat quickly away from where it is not wanted, as in the cylinders of a motorcycle engine. On the other hand, poor conductors, or insulators, are used to impede the flow of heat. Cooking utensils often have wooden handles. So also does cutlery. Oven gloves made of cloth are used for handling hot dishes. And mats are used to protect the surfaces of tables. Lagging is put around cold water pipes to prevent them from freezing in the winter. A feature of many materials used as insulators, like glass wool, is that they have a lot of air trapped within their structure, and air is a very poor conductor of heat. Nature has provided many animals with this kind of insulation. Sheep's wool contains a lot of air trapped between the fibers, and the fur, feather, and down of other animals all contain some air. Even the hairs of our own skin trap a thin layer of insulating air next to our bodies. String vests keep us warm because they increase the depth of this layer, trapping air in the holes of the net. Woolen sweaters keep us warm, mainly because the fibers themselves are good insulators. But some air is also trapped between the fibers and between the sweater and our bodies. Some of the most important uses of insulators are those which enable us to economize on valuable fuel. In cookers, for instance, insulation helps to reduce cooking. More pressure and so gravity will fiber the principle to be within inside is living insulated wastage just like is transferred with many materials heat